All right, here we are at lecture 7, topic of continuity. Let's get right into it. Continuity, I'm going to have an informal definition right here. A function is called continuous at a point A when the graph doesn't contain a break at the point or a jump at this point, the point with a coordinate A. This is a very intuitive notion if you're looking at the graph of the function. I have an example of a graph here with all sorts of discontinuities that you could have, but I also have some points indicated where the function is actually continuous. So I singled out 6 points in this graph. And if you look at it, you will see that the function is continuous at the points A1 and A2. If you're just looking at the ones that I'm mentioning, that is only those 6 points. And discontinuous at the others, A3 through A6. According to this informal definition, because if you look here, the graph above A1, there's no problem in there, no breaks. Even above A2, where the graph has a sharp corner, if you've studied calculus before, you'll know that this is a problem later when we are studying the derivative. But if we're just talking about continuity, the graph is continuous there. It doesn't break, it doesn't jump. Now, A3 is a point of discontinuity because there is no value defined for the function. So there is a hole in the graph. And at A4, there is also a hole. The only difference between A4 and A3 is that there is a value defined for f of A4. But that value is not, you can think of it as it's not consistent with what the graph was, with what it wanted to be. Because of this hole there, we say that the function is discontinuous at that point. A5 is an example of what's called a jump discontinuity. The graph was coming towards this height here as it was approaching A5 from the left side, but suddenly the value of A5 is much smaller. It jumped all the way down suddenly. And A6 is what's called a asymptote discontinuity, simply because the graph is going towards plus infinity in there. Even if there was a value associated to A6, this would be a discontinuity. So this is the informal notion of discontinuity, which you can get from a graph. And continuity is where the breaks they don't happen. So continuity is when it does not contain a break. How do we understand a more formal way to talk about continuity? The answer should be using limits. The reason why, for example, A4 is a point of discontinuity is because the value of the function at A4 is not what it should have been according to the graph, which is the limit as x approaches A4. So we want to say that there is continuity when the value at the point is equal to the limit as you approach the point, which means that both of that value must exist and also the limit must exist. So here is what our definition of continuity is going to be. A function is called continuous at a point A if all of the following 3 conditions are true. The value must exist, the value of f of A. The limit must also exist, and those 2 things must be equal to each other. So this is the connection between continuity and limits. This is actually the reason why we study limits. You can think of it that way. One of the reasons, at least. And why are we studying continuity? Because the useful tools that we are going to develop later, the tools of derivative and integrals, they basically only apply to continuous functions. A lot of functions in real life applications are actually discontinuous, but that's not really a big problem. They can usually be approximated by continuous functions. A lot of models, like physics problems, for example, they are modeled by continuous functions. And even the functions which are discontinuous in real life, usually they are discontinuous at just 1 or 2 points, and between those they are continuous. So calculus is a very useful tool to study functions from real life as well. But continuity is going to be a requirement. So here's a quick easy problem for us to understand this definition. I have a function, I'm giving you 3 points, 1, 2, and 3. Determine if this function is continuous or discontinuous at those points. So what is happening here? Solution. F of 1 and f of 2, both of those numbers do not exist. You can say it like that, or you can say the function is undefined at those points. Why? Because of the denominator. You cannot divide by 1 minus 1 or 2 minus 2. So even though if you factor this numerator here, which you don't have to do, but if you wanted to do that, this would be a minus 2 and plus 3. No, sorry. Minus 1, minus 4. Yes. So if you factor this the numerator, you see that canceling this x minus 1 would give you a simpler expression. This type of procedure is useful if you're computing a limit, but the function itself is not the canceled form. You cannot say that this is equal to x minus 4 over x minus 2. The function was given in this form for whatever reason, wherever this function came from. So the function is not defined at the number 1. If you tried to graph this function, you would see that around the number 1, it simply has a hole. It's just not defined there. So f is discontinuous at those points. At 1 and 2, because it's not defined. But at 3, you're going to see that basically there are no problems at 3. Look back at the conditions. F of 3 exists. We can find f of 3. The limit is also going to exist. How do you compute a limit as x approaches 3 for this expression? Well, this is an expression for which there are no problems. You're not going to run into trouble of dividing by 0. You can plug in 3. And the value that you're going to find for the limit, well, if you can just plug in 3, then the value will be f of 3. So I'm just going to write all of those things in here. F of 3 exists. It is actually equal to whatever this number will turn out to be. 3 minus 1 times 3 minus 2. So this looks like a minus 1. Unless I'm doing this wrong, but this doesn't really matter. Limit also exists. And how do I know it exists? Because the third condition is satisfied. The limit is just going to be, again, plugging in 3 into the function. And that's f of 3. So f is continuous at the number 3. And this is always going to be the case. Whatever function you write down, using the expressions that we know, exponentials, polynomials, all of that, it's always going to be continuous at the points where it's defined. But we're going to have theorems that guarantee that for us. But now here's one example of a function that is not continuous. You may have encountered this already, but we haven't specifically talked about it, so I'm just defining it in here. The floor function, also called the largest integer or integer part function. You have this symbol for it. The definition of the floor function is the floor of x is the largest integer that's less than or equal to x. Imagine the real line, x is somewhere in there. You're going to be looking at the largest integer that you can find to the left of x. I have just a few examples here. The floor of integer numbers like 3, 0, or minus 2, those are the same as the numbers themselves. The floor of a fractional number like 5.1 will be the integer part of that, 5. 1/4 is 0.25, the integer part is 0. Pi is 3.14, so the integer part is 3. But just be careful about negative numbers. The floor of minus 5.1 is not minus 5, it's minus 6 because of the real line again. If minus 5.1 is here, then this would be the number minus 5, and this would be the number minus 6. You see that the largest integer that's less than or equal to minus 5.1 is actually minus 6. All right, so this is the floor function. What does it look like in a graph? Floor of 0 is 0. Floor of anything between 0 and 1 is also 0. But then floor of 1 is 1, not 0. Now, floor of numbers between 1 and 2 is all 1. But floor of 2 is 2. So this function actually extends like this. It's a bunch of steps. Just keeps going like that. Minus 1, minus 2, minus 1, minus 2. That's the floor function. You can see from the graph that it has a lot of points of discontinuity, which are the integers. Floor of x is discontinuous at all. Let me write it this way. N belongs to z. Z is the set of integer numbers. So what this means is all integers n, which are the numbers 0, 1, 2, 3, 4, but also the negatives, -1, -2, -3, and so on. Why is it discontinuous, you may ask? I mean, the value of the function is defined. The function has a value at those points, but it doesn't have a limit. The limit of floor of x as x approaches an integer does not exist. You can again just see that from the graph. For example, at the number 1, if you approach from the left, you get a 0. If you approach from the right, you get a 1. So this is an example. It's basically the only example that we can write with formulas other than quotients. You know, when a quotient is undefined, or like a logarithm which is undefined. But this one is the only example that we know with formulas that gives you a function that is defined at the points, but just discontinuous. All right, now this is the theorem that I was talking about, the continuity laws. They reflect the limit laws. They should feel very intuitive, very straightforward. Let's look at what they're saying. If you have two functions f and g, which are continuous at a point A, then every one of the following functions is also continuous at A. F plus g, f minus g, f times g, and then in particular, the second one here, constant times f, where c is any constant. So all this is going to be continuous automatically. Now quotients are going to be continuous as long as the denominator is not a 0 at that point. And finally, raising to any positive integer power. We have to say positive here because if it's negative, f to the minus n, you know that, let's apply that to a point. That means 1 over f to the n. So if you were allowing a negative exponent, then you have to worry again about whether f is 0 or not, because now it's a denominator. So I'm not even writing that in here as a theorem. Just wanted to mention these ones. All of this is a consequence of limit laws. Just a quick example. For the first one, for f plus g, let's say, if both f and g are continuous, that means that as you approach a in a limit with f, the f function, the value that you find is f of a. And if you approach a in a limit with the g function, the value that you find is g of a. So we know those by hypothesis in this theorem. They are telling us f and g are continuous. And now we're trying to understand why f plus g is continuous, for example. Why is that true? Because if you try to compute a limit of f plus g, we know from the limit laws that the limit of the sum is the sum of the limits. And each one of these is equal to, the first one is f of a, the second one is g of a. So that's the value of the f plus g function at a. So this is what I mean by they are a consequence of the limit loss. The limit of the sum is the sum of the limits, gives you what you need to get continuity. Just so if you were curious about where this theorem is coming from. Now, why do we care about that? For example, read this first example here. The above theorem implies that if you have a rational function, p over q, where p and q are polynomials, this is automatically going to be continuous at all points where q is not 0. So yeah, why is a polynomial function continuous? For example, the p function, let's say. Well, it's a sum of powers of x with coefficients in front. All of those are continuous functions. So p is continuous, q is continuous, and the theorem tells you that p over q is also going to be continuous at the points where q is not 0. So there you go. We already knew this. It's just we're using different words now, but we already knew that if you're trying to compute a limit of rational function, it's always okay to plug in the number a as long as what you get in that rational expression is well defined, which means the denominator is not 0. We already knew this, right? That's essentially what we are using in this. So here is a quick problem about this. What are the points where this function is continuous? Solution. Once again, you cannot cancel the x here in the expression of the function because you don't know if x is going to be 0 or not. If x is 0, the function is just not defined, right? You cannot cancel the x, which makes it suddenly defined at 0. But that's not the same function anymore. F, for whatever reason, it came in this form and it's not supposed to be defined at 0. So when you look at this function, what are the points where it is continuous? The solution is every point where the denominator is not 0. Solution, all points such that x times this quadratic expression is not 0. Well, where is it going to be 0? Where does that happen? So how do you solve this equation? It's already given to you in a form of a product, x times something. So you can have either x equals 0 or that rest of the expression equals 0. And this is a quadratic that you can factor with minus 1 plus 5. 5 minus 1 is plus 4. 5 times minus 1 is minus 5. So these are the numbers 0, 1, and minus 5, which make this expression equal to 0. The solution that we're looking for were the points where that was not 0. So the answer, you can write this answer in a few different ways. You can say all numbers different from these 3, where the function is undefined, or if you want to give interval notation for it, you want to basically take every single real number except for those 3. Minus 5 should be the first one appearing here. In order, minus 5 is the smallest of those 3. The next one is 0, then 1, and then you can go off to infinity. So if you take the real line and remove 3 points, minus 5, 1, and 0, then you have a union of 4 intervals. 1 and 0 in this order. Now this is right. Yeah, so this is how you could write the solution in interval notation. So now I'm going to give you 4 very similar problems. Again, just intended to make us really understand what continuity means. With a piecewise function this time. Here's the first problem. What are the points where this function is continuous? What's happening to this function is it's defined by 2 polynomials, which are continuous functions, but they're supposed to be joining at the number 3. So it's a piece of polynomial first and then some other piece of polynomial later. Just by looking at it without thinking too much, here's the number 3 is where the function changes behavior. It's some form of linear function first, and also it is that value at x equals 3. But then after that, it's going to be a parabola. And just looking without thinking, we don't know if that parabola joins at that point or not. I mean, it's very easy to figure out. That's essentially what we're going to do. But I'm just trying to point out what could be the problem with a piecewise function like this. The 2 pieces might not join at the same location, which means you're going to have a discontinuity at that point. But at all other points, it is continuous. So we have to write that at least. F is continuous at all numbers, maybe a different from 3, because at each one of those numbers, f is a polynomial around those numbers. Any such number. But we have to analyze what happens at at a equals 3. So what about a equals 3? Remember the 3 conditions that need to happen. First of all, f of 3 needs to be well defined, and it actually is. According to the formula, if x is less than or equal to 3, in particular if x is 3, f is supposed to be 5x minus 2. So this number is the number 13, it's well defined. But now what about limit as x approaches 3? Does that exist? It must exist. And if you remember from our limit lectures, how do you compute this one? It's a piecewise function. You need to come from both directions to see what happens. Each one is going to be very easy. If you're coming from the left, then you need to use the expression 5x minus 2, giving you a value of 15 minus 2, which is 13. And if you're coming from the right, then the expression for the function is the parabola x squared plus 4. But what does that give you? If you plug in 3, it actually gives you 9 plus 4, which is 13. So you found the same value for the lateral limits, which means, yes, the limit does exist. That was everything that we cared about in this second item. But in the third item, remember what that one was. That's the important one. The limit, it's not only that it must exist, but it must be equal to the value of the function. And we can see from the work above that that's actually happening. Both of these, we found both, and they are 13. So yes, f is continuous at 3. Going back to my little drawing of the graph, what is actually happening is that the linear part and the parabola part, they join together at the same point. So there is no break in the graph. Now my next example with a piecewise function. What changed here? Let me go back to the previous one. What changed is that this time there is no value for f of 3. Look at the conditions. The 2 formulas for f the places where they happen, they don't include the number 3 this time. So you should already know what the answer is at the number 3. The function is not continuous at 3 because there is no value for it. F is discontinuous, discount at 3 because you can say f of 3 does not exist. But f is continuous at all other points. I'm not going to write the justification this time. It's the same as the previous one. At any other point, the function is well defined as just one polynomial expression, and that's continuous. So what happens to the graph of this function this time, it's very similar to the previous one, but there is no value for the number 3. So that's a break in the graph. Next example, piecewise function. It's very similar to the previous one, but I'm giving a different value for x equals 3. There is a value, it's minus 20. What are the points where this is continuous? Again, f is continuous at all points, all a different from 3 for the same reason as before. But what's happening at a equals 3? This time, f of 3 exists because it's minus 20. The limit still exists. Limit of f of x exists, and the actual value is 13. How do we do this limit? It's going to be the same as the first example. The value of minus 20 is irrelevant, remember? The value at the number is irrelevant. You have to do a lateral or one-sided limit using the two expressions before 3 and after 3. And it's the same calculation that we did. You find the number 13. So both of the first two items are satisfied, but as you can see, the value of the limit is actually not the value of the function f of 3. So if you wanted, like, this is a green check mark, but this is a red X. Third condition is not good, so f is not continuous at the number 3. What does the graph look like? Something like this. At the x value of 3, you have a value of minus 20 all the way down there. So again, that's a break in the graph. Last example. This compares to the first example. The only difference is that now this is x squared plus 7 instead of x squared plus 4. Where is this function continuous? I'm once again writing that it is continuous at all numbers different from 3 where the break happens. We just need to analyze 3. F of 3 exists according to this graph, to this formula. It's 13. That's similarly to the first example. Limit, however, does not exist. That's where the problem happened. How do I know it does not exist? Well, again, you have to analyze the one-sided limits. This time, because of this plus 7, there will be a difference between them. So once again, from the left, what was it, 5x minus 2? This is 13, but from the right, if you plug in a 3 into the expression x squared plus 7, you have a 16. These are different values, so the limit does not exist, which means f is not continuous at 3. Did I write it correctly? Yes. What is the graph doing now? Once again, there is the linear part, and the value of f of 3 is given by the linear part. But then the parabola joins a little too high. the graph is jumping. Now, okay, we are basically going to skip these concepts. I'm just going to mention them very quickly. A few book problems will ask you specifically about them, and they should be very intuitive. Just like we can talk about continuity, you can also talk about right continuity and left continuity. And basically, the three conditions now, the only thing that changes about them is that you're going to have a lateral limit. So I'm not even going to read this other than the three conditions. What does right continuity mean? At a point A, it means that f of A exists and the one-sided limit from the right exists. And those two numbers need to be equal. Similarly for left continuity. And here is my quick example. What's happening here, I gave you 4 points. Let's call this function f, this graph here. F is both right and left continuous at the number a1, for example, because it is continuous. By the way, if you have both right and left continuity, then you have continuity, just like with limits. So as you can see in this, around this point, there are no breaks, either if you're coming from the right or the left. Now what is happening at A2, that's the one where only one side, continuity will happen only from one side, and it's from the left. What happens here is that the value of f of A2, which is where the filled in circle is the same as the limit from the left. But the value is not the limit from the right. The limit from the right is this open circle. So because of that, f is actually only left continuous at A2. Now similarly, look at A3. The two sides reverse role. F is only right continuous at A3. And what is happening at A4? Neither condition will be satisfied. The limit from the left is given by this open circle. The limit from the right is given by the other open circle. They are different. But neither of them is the true value of the function. F of A4 is larger than both. So f is not anything. It's not left or right continuous at the number A4. And the example that we've already talked about is the floor function. The floor function is right continuous at all points, but only left continuous at the points which are not integer. Let me again just draw the graph so we remember that it looked like this. So you see that if you're talking about right continuity, no matter where you are, no matter if you are at one of these points which are non-integer points, or maybe a point which is integer, at either of those points, if you're coming towards those points from the right, the function is approaching the actual value of the function, which means right continuity happens at all points. But left continuity is not going to happen at those breakpoints. That should be obvious. Coming towards any one of these, like A3, from the left will give you a value that's not the true value of the function. So you only have left continuity at the other points, like in the ones which are meeting the pieces of the graph which are horizontal lines. In other words, points which are non-integer. So that's our example of a function that has right continuity, but doesn't have left continuity at all points. We can probably skip this. I'll leave this on the screen here if you want to copy this down. We're not really going to use this. The book might use it. They will ask you for intervals of continuity in some problems. In case you're curious, this is what they mean. But really, this is irrelevant. Now, this is going to be important to know. We're simply not going to prove any of this other than by drawing graphs. Well, I'm basically saying that these functions are continuous wherever they are defined. We know we use these functions all the time. Exponentials for positive base, logarithms for a positive base, trig functions, sine and cosine, and in particular, everything that you can construct from them, and square roots or cube roots, fourth roots, n is integer. So all of those functions are continuous. And what does that mean, by the way? What does it mean to say a function is continuous? It means continuous at all points where they are defined. That's exactly what I'm saying here. They are continuous at all points A, where they are defined, or you might have to use lateral continuity in case they are only defined if they stop being defined somewhere, which is the case of this root function for a even n. So let me just show you what I mean. I mean, the way that to justify this informally is just by saying, if you draw the graphs of these functions, you see there are no breaks anywhere. But in particular for the nth root function, here's the graph of the square root function. You should know that it looks like this. A actually is not defined for x less than 0. So if you're going to be talking about continuity of the square root function, it is continuous at every point. And it's also right continuous at the point 0. You don't really talk about continuity there, but right continuity, because you can only approach it from one side. But it's true that if you approach 0 from the right with the square root function, you find a 0, which is the value of the function there. So it is right continuous. Okay, so you can use this fact in all problems that these functions are all continuous. And where do we need to use that? We need to use it essentially when we have composition. The theorem is right here. If you want to, in formal language, kind of, this is formal language. If you have two functions and you're going to be composing them, as long as you're looking also at a specific number a. So the first function g, remember that this composition applied to a means f of g of a. If you're computing this expression, you're computing first g of a, and then you're computing f of that. So if g is continuous at a, and then f is continuous at this point where it is applied, which is the point g of a, then the whole thing f circ g is continuous at a. For us in calculus, why is that important? Why does that matter? It matters because it allows us to say things like this. Essentially, writing a limit inside. As long as the function that's outside is continuous at the point that gives you that limit. So limit of the square root is square root of the limit, as long as that limit inside exists, which is the case in here. Like if you wanted to compute this, it would be 2. What is happening here? We have a composition of two functions in this example. Imagine the f of x is square root function, and g of x is the one inside, x squared plus 3. The expression that we are looking at is f of g of x. Now, because g is continuous at the point 1, and f is continuous at the point g of 1, which is 4, then the whole expression is continuous at 1, which means if it is continuous, you can compute a limit by plugging in the whole expression, by rewriting 1 in place of x, which is essentially what we did here. So now let's read this more generally part. This last two lines here. If you have a inside function g, which has a limit L, and your outside function f is continuous at that L, then when you're trying to compute a limit like this with a composite function, you can write the limit inside of the L function. And just rewriting the limit of the g function inside, rewriting that as L. So the final answer of that limit will be f of L, just like in this example above. The limit of g was 4, the limit of f of g was f of 4, which is square root of 4. Now, we don't really need to worry too much about this result. We've been using this already. Whenever I told you, if you're trying to compute a limit, whatever, let's say it's x squared plus 5, and then the whole thing raised to 3. I told you, as long as you can plug in the number, then you can do that. Then that's how you compute the limit. In this case, 9 to the third. Right, we know this already. What is going on behind the scenes there? That's this theorem here. What is actually going on is exactly this. The particular example that I just gave you is a composite function. The outside function is the 3, and the one inside is x squared plus 5. What are we actually saying is that, first of all, g of x has a limit. It's 9. And f is continuous at that number 9. Because f is the cube function that's continuous everywhere. So because of that, if you want to find the limit of f of g, then that is the same thing as f of the limit of g, which is f of 9, as we just did. F of 9 is 9 cubed. So I just want you to think of this theorem as a kind of behind the scenes. It's a justification for the procedure that we do all the time of just plugging in the value whenever it's possible. But why do we have to be careful about this sometimes? We have to understand what we really mean by whenever it's possible. What we mean is continuity of the functions. In particular, let me just give you one final example where the outside function now can give you some trouble. Again, it's the floor function. So this is my last example for today. A student wrote the following two statements, A and B. Both are limits. The only difference is the sign changing to cosine. Look at what they wrote in the first one. You have the function 2 sine x, and the whole thing is inside of a floor. The student wrote the limit symbol inside of the floor. And then he just computed the limit inside here. Well, 2 sine x. Sine x is going to sine of pi over 6, which is 1/2. So you have 2 times 1/2 inside of floor, and that's floor of 1, which is 1. And the student did the same thing for the cosine. Put the limit inside. Now cosine of pi over 6 is root 3 over 2. And 2 times root 3 over 2 is root 3. And the floor of root 3 is actually 1, because root 3 is like 1.7 something, approximately. So that's what they wrote. Which one is right, which one is wrong, and explain. So what do you think? How do we think about this? We need to understand that you can do this procedure of taking a limit inside as long as the function which is outside, which is the floor function here, is continuous at that point, at that limit. So remember that this is continuous only at non-integer numbers. So if you look in item B, the limit inside is root 3. This is root 3. That's a non-integer number. So for B is correct because we can do this procedure of taking a limit inside of a function because this outside function is continuous at root 3. So that limit is correct by the theorem that we just mentioned. But A is incorrect because this time the limit inside is actually an integer. I mean, that the whole reason why I have the number 2 here was to make this number an integer. It's the number 1. And that function is discontinuous at 1. So in principle, I mean, the answer might be that one also, although it is not. But the way the theorem was applied is wrong here. You cannot do that. And in fact, as I told you, this limit does not exist. The first one, you should try to think of it. Try to compute the one-sided limits for it, if you're curious. So the lesson to take from here is, if you don't have continuity, then you need to be very careful about this idea of, if you're trying to compute a limit, you just plug in the value, which is essentially what this student is doing here. Be careful with that. And when do we know that we don't have continuity? Things like this, the floor function or piecewise defined functions.